So modern atomic theory. Atomic theory is the idea that all matter is composed of atoms, and it grew out of three laws. The law of conservation of mass, the law of definite proportions, and the law of multiple proportions. These were laws. These were things that were observed but not explained. Atomic theory explains these laws, so we're going to talk about each of these. So the law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. And this came from Antoine Lavoisier and his experiments of burning things in closed containers. Right? We talked about that the first day. What this means is when a chemical reaction occurs, the total mass of the substances involved in that reaction doesn't change. The law is consistent with atomic theory. Atomic theory explains this, saying that what's happening in a chemical reaction is that the atoms are rearranging. We're not making new ones. We're not destroying any. It's like building stuff with Legos. If you start with 100 Lego bricks, you're going to end up with 100 Lego bricks, right? The mass of them is the same because they are individual, indestructible particles. So atomic theory explains the law of conservation of mass. Here's an illustration of it. Here we have sodium metal, which is soft enough that you can cut it with just a regular table knife. And we can illustrate it this way so that each of these purple spheres represents a sodium atom. And they're just all arranged like this, and we've got a nice crystalline solid. So let's start with 7.7 grams of sodium and mix that with 11.9 grams of chlorine gas. Chlorine gas is composed of these little molecules, each containing 2 chlorine atoms. When these combine, they form sodium chloride, which has very different properties. Sodium metal reacts violently with water. Chlorine gas is very toxic. You mix them together, you get sodium chloride, which tastes really good on a steak. Right? Too much of it will kill you, but not enough will kill you also. We need a moderate amount. We don't really need any sodium metal or any chlorine gas. We have absolutely no need for those. But combined, there's something different. The mass the sodium chloride produced is going to equal the total mass of the substances used to make it. Because we're taking the little purple balls and the little green balls and we're just arranging them differently. That is what happens in a chemical reaction. We can't see that happening, but that's what's happening. Everybody okay with that? We're rearranging particles. Law of definite proportions. French chemist Proust in 1797 made some observations. He summarized his observations in what's known as the law of definite proportions. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. He did not know exactly what atoms were, but he observed that if you get water from your faucet or water from the ocean and purify it, or water from the Nile River, no matter where you get the water, the ratio of oxygen to hydrogen in it is always the same. So as an example, if we take 18 grams of water and decompose it, break it into its individual elements, that's actually quite simple to do. You can just use a battery. You'll get 16 grams of oxygen and 2 grams of hydrogen. So we can look at a mass ratio. Take the mass of oxygen, divide it by the mass of hydrogen, and that gives us the value 8, or expressed as a ratio, that's 8 to 1. So 8 grams of oxygen for every 1 gram of hydrogen. It's always going to be like that. The ratio is important because the ratio doesn't depend on the size of the sample, how much water you started out with. So this is a sort of a problem that you could be asked to do. And sometimes these really trip students up because you try to make it much harder than it is. So 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. So we have two different samples. They're each giving different masses of oxygen and carbon. Show that these results are consistent with the law of definite proportions. The law of definite proportions says that the ratio of oxygen to carbon in each of these samples should be the same. We don't need to know chemical formulas or molar masses or anything like that. So we've got sample number 1, and that one has 17.2 grams of oxygen, and I'm going to divide it by the mass of carbon, 12.9 grams of carbon. Why am I doing oxygen to carbon and not carbon to oxygen? There's no fancy reason. I just like ratios that are larger than 1. So I'm going to take the big number and divide by the small number, because I think they're easier to look at. So this will give us 1.333333333333. Repeating forever. Let's use our knowledge of significant figures. 17.2 grams, that's a measurement. It has 3 sig figs. 12.9 grams, also a measurement, 3 significant figures. This result should have 3 significant figures. So that's our third sig fig, and then I'm just going to write the next 2 digits down because that's what I do. So there's our ratio, 1.333. 1 1/3, really. So let's look at sample number 2, and we're just going to do the same thing. We're going to take the mass of oxygen, 10.5 grams of oxygen, and divide by the mass of carbon. This sample must have been smaller in size originally, and that's why there's less oxygen, but there's also less carbon. And so we do that on the calculator, and this should also have 3 significant figures, so there's the first 3, and then the next 2 would be 2 and 4. My calculator did not give me the exact same number, but these would be considered to be the same. When we round them according to the rules of significant figures, they do come out exactly the same. They are not perfect because measurements were involved, but the ratio of oxygen to carbon is the same in all samples of carbon monoxide. Any questions? Let's look at the law of multiple proportions. And if you just look at these names, they seem to contradict each other, right? Definite proportion and then multiple proportions, what is that? So John Dalton again, 1804. There's different ways to express that, and all of them are confusing, but this is the best one, I think. When 2 elements, we're just going to call them A and B. When these 2 elements form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So what does that mean? It actually takes a lot of words to explain what that means. So an atom of A, let's just look at 1 atom of A. It can combine with 1 atom of B. It could combine with 2 or 3 or 4 or 17. But you can't have 1 atom of A combining with 1.5 atoms of B, right? It's like choosing teams or something. You have to have whole numbers of people, right? Because you can't divide a person in half. I know the magicians do it. I don't know how they do that, but it's an illusion, right? You have to have whole numbers of atoms. Building something with Lego bricks, you can use 1 red brick and 2 blue bricks, or 1 red and 3 blue ones, but nothing in between. So what happens is we take the ratio, like we did for definite proportions, of each of those compounds, and then we do the ratio of the ratios. I know this is confusing. And the ratio of the ratios always ends up being a small whole number. Something nice like 2 or 5. It's really kind of crazy. So let's look at carbon monoxide and carbon dioxide. both composed of carbon and oxygen. The mass ratio of oxygen to carbon in carbon dioxide is 2.67 to 1. So we do that ratio just like we did. Whatever the actual mass is of oxygen divided by the actual mass of carbon, and we get a ratio of 2.61. That means 2.67. 2.67 grams of oxygen reacts with 1 gram of carbon. In carbon monoxide, and that's the example we looked at for definite proportions, we had a ratio of 1.33 grams of oxygen to 1 gram of carbon. You might say, yeah, I'm not really seeing any whole numbers right now. What's going on? Well, this is the ratio for one compound. This is the ratio for the other compound. We need to do the ratio of the ratios. So we take the ratio of this one for carbon monoxide. And again, I'm just choosing the big one on top because I like large numbers. 2.67 divided by 1.33, and we come up with 2. And if you looked, I can't think of any other compounds between carbon and oxygen off the top of my head, but if there were, and you did the same process with them and did ratios, you'd end up with small whole numbers. Any questions about that? What this number 2 is telling me is that this compound has twice as many oxygen atoms as this one. So how do we do a problem? It'd be something like this. So hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms 0.125 grams of hydrogen for every 1 gram of oxygen. And if we do the same thing to hydrogen peroxide, it forms 0.25 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So that says what we need to do is we need to take the ratio or the mass of hydrogen combining with 1 gram of oxygen for the first one and make it a ratio with the second one. I'm going to put the second one on top because it's larger. So we've got 0.25 grams of hydrogen per 1 gram of oxygen, and I've got 0.125 grams of hydrogen per every 1 gram of oxygen. And you do the math and it comes out to be 2. It's not always 2, but it's a whole number. Any questions? The ideas here are important. Being able to actually do this problem, not such a big deal. So now that we talked about the 3 laws that the atomic theory explains, let's talk about Dalton's atomic theory. So he explained those 3 laws with these ideas. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios to form compounds, and atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. They can't be changed one into another. Now, this word chemical in here is an important modification. In a chemical reaction, okay, that is specifically excluding nuclear reactions. In a nuclear reaction, one element does change into another, and all kinds of craziness ensues. That's like playing with Lego blocks and using a hacksaw, okay? And you're like sawing the bricks in half. It's not normal, right? That's not regular stuff. We are not talking about things like that here. We'll get to this later in the chapter, but statement number 2 here is not exactly correct. It was discovered that they do vary a little bit in mass, and you don't throw the baby out with the bathwater. You don't just throw out the entire theory. You modify the theory. So there were some inconsistencies, some things that weren't quite right with his original theory. We needed to throw the word chemical reaction in here. so that we could get away from the nuclear stuff. We just tweak the theory, we adjust it, we fine tune it.